All right, we can just give it maybe another 2 minutes or so just to see if anyone else joins, and then we can get started. All right, so it seems like we have a few people on this call. We can go ahead and get started now. So thank you all for joining us again. This is the third part of our TSMA Statistics 101 series. And so we're gonna go ahead and get started and kind of pick right up where we left off last time. And so I'm gonna go ahead and share my screen. I have Stata pulled up, and we can go ahead and get started. Okay. Can everyone see my screen? If you can't see my screen,
Yeah.
say, okay, perfect. Got it. Um, all right. So for everyone who was here last time, which hopefully most of you attended the prior session, because we'll be building off of the prior session's code and analysis and working with that this session. Um, but just as a quick recap, so what we did last time was we essentially created this do file together. I literally just opened it up, haven't done anything with it yet. Just opened it up, haven't even run it yet. But essentially what we did was we imported the data set, and we're using some fake data that's modeled after UNOS data for this tutorial. We changed our directory here, telling Stata where to put all of the outputs from our Stata do file. We applied some inclusion exclusion criteria. And again, these are very similar to UNOS variables. And so if you're doing UNOS work, this is what it's very similar to what your code would look like. But if you're doing work with other databases, obviously you're going to change the variable names here. We then started cleaning the data set. And so just as an example, we did recipient age. We cleaned that by essentially just relabeling our age variable here, giving it a name here, a label. We recoded recipient sex. And so we took this original variable in the UNOS database called gender. We created this new one, recipient male, essentially rec male, and we made rec male 1 when the gender was coded as male or coded as M. We made rec male 0 when the gender was coded as F. So essentially we turned this string variable into a binary 1-0 variable, and we labeled this variable recipient male. And then we also cleaned recipient race. And so we took the original FCAT variable, we created our own version of this. We did some regroupings of the race to what we want it to be for analysis. We created a race label, and we applied the race label to our recipient race variable here. And if anybody has any questions at any point, feel free to just unmute and ask, or throw it in the chat. And we can have maybe Isaac or Emily or Carter, someone monitoring the chat for questions.
Absolutely.
Okay, perfect. So we're going to just go ahead and move forward with what we have here. So as a recap, in order to run your code from the do file, you highlight everything you want to run. And on Mac, you do Command D. On Windows, you hit Control D, I assume, and then you can also highlight and push this run button here, or this execute button. So we've just executed it. We ran all of our code, and we can see that it ran because we can see the commands in the command window. We can see the variables over here on the right. We can also see some of the properties have changed. So we can see that this database has 12 variables, 38,000 observations after applying exclusion criteria. And so we know that our database is fully loaded, ready to go. So I'm just going to move forward with the next part of our code. And so what we want to do next is we want to start cleaning some outcomes variables, because I do want to show you guys how to run some analyses. And so in order to do that, we're going to create some outcomes variables. So I'm going to create some variables, or I'm going to clean some variables that we commonly use in our lung transplant analyses with UNOS. So one of them is intubated at 72 hours. This is a variable that we have in our fake data set here, intubated 72 hours. What we can do is we can actually take a look at it. So we can, I'll write this here. We can tabulate, which if you remember from last time, will just give us an overview of what the data looks like. So if we run that code, we see that intubated at 72 hours, essentially this outcome is looking at whether or not recipients were intubated at 72 hours post-transplant. So like still intubated at 72 hours post-transplant. And what we can see is that 5,000 of them, so about 31% of them were still intubated at 72 hours. 12,000, so 67% were not intubated at 72 hours. We do have some unknowns as well, so 342 unknowns. And remember, the other thing that we want to do is we want to make sure that we're always looking for missingness in our variables. So something I like to do is I like to essentially write the same code, but comma M. And then if you run that with comma M, you can see how many are missing. So you'll actually see that for this variable, we have about 20,000 with missing data for this variable. And that's because this variable only really started with UNOS, or started in the UNOS database, I think around 2015 or so. And so it's really only those, the last decade or so of data that where we have intubated at 72 hours. And so that's just something important to know for your analysis. So in this case, for example, we started in the year 2000, but this outcome variable is only going to be applicable to people after 2015. And so that's just something to know. But for the purposes of this demonstration, we're just going to continue ahead with this. So if I want to clean this, I essentially want to turn this from a yes, no, unknown into a 1-0 system. So how I'm going to do that is very similar to how we cleaned the prior data. So I'm going to generate a new variable. I'm going to call it int 72. I'm going to make it 1 if intubated 72 hours equals yes. And so essentially I'm creating a new variable to make it 1 if the original variable equals yes. I'm going to replace this new variable with 0, because essentially it's a 1 if intubated at 72 hours is a yes, and everything else it's a missing for now. So I'm going to replace int 72 with 0 if intubated at 72 hours equals no. And then essentially everything else should be missing. So all the data that's missing right now is still going to be missing in our new variable. All the data that's marked with a U for unknown is also going to be missing in our new data, in our new variable. And that's exactly what we want it to be. So if we run this, and now just to check it, we look at what the variable values are. What we'll see is 12,365 that are no's, which corresponds exactly with what we're expecting here. And then we also see 5,758 yeses, which again corresponds exactly with what we're expecting here. And then everything else is missing, which is why this the total number is it's 342 subtracted from 18,465. So that's exactly what we were expecting. We do want the unknowns and the missings to stay as missing for this variable. And then like I did for all these other variables, we want to label this variable so we know what it is. So I'm going to label value let's see. So I'm going to create a new label here. So I'm going to label define, yes, no label as, actually we can just call it incubated 72 label. We'll say 1 is yes, and we'll say 0 is no. And then essentially once we define that, we want to apply that new label. So we're going to label variable 72 and 72 label. So we're gonna apply that. Oh, sorry, label values here instead of variables. And 72 underscore here. And then that should run perfect. And then now we can tab this again. So if we tab in 72, we now see it's no and yes, as opposed to before it was 0 and 1. So that's exactly what we want. We now want to label the variable to give it a good helpful name, like incubated at 72 hours post, for example. And then we can run that. Okay, good. So now if we just take a look at it again, we can see it's the name of the variables here, the values, the names of the values are here. So 0 being no, 1 being yes. And this is exactly what we want our data to look like. So now we've cleaned this first outcome variable. So I'm just gonna outcomes. The next outcome variable that I want to clean is post-transplant length of stay. And this variable here is coded as LOS here. And so we can actually take a look at our data. Remember, BR to browse, and we can look at length of stay here. And so this is the length of stay variable. Let's see. So if we take a look at it, it's essentially what we can see is it's post-transplant length of stay in the hospital. And we can see it's in days here. So this patient, for example, stayed for 41 days post-transplant. This recipient stayed for 10 days post-transplant, et cetera. So we can take a look at what it looks like for now. And so remember, with these containers variables, we want to summarize this variable. So we can summarize LOS. If we add the D, it's D for detail. And so what we see is we see a more detailed summary of length of stay. We see the mean is 27 days, standard deviation of 33 days. Remember, this is all fake data. So this is not actually reflective of actual mean postoperative lengths of stay. The median in our data set is 18 days. Smallest is 0, largest is 45, 48, 491, 562. So the range is essentially 0 to 562. So now that we know what this data looks like, honestly, it's pretty clean. So what I'm just going to do for this variable is I'm just going to give it a name here. So I'm going to label this variable. I'm going to say post-transplant hospital length of days. I'm just going to label that variable, and then we can move on to the next variable. So the next one I'm going to demonstrate is looking at essentially survival analysis. So looking at death, mortality. And in UNOS, the way it's coded is that every recipient has a value for P time, and P time essentially indicates last known time of follow-up. So there are two variables here. So if we take a look at the data, what we see is P time. There's one P time and there's one PX stat. And the way that this works for UNOS is that the P time tells us when this last, the point of last follow-up was, I guess, how many days post-transplant the point of last follow-up was. So this one was 424 days post-transplant. And then PX stat essentially tells us what that last follow-up was. So D for death, D for died, A for alive, L for lost to follow-up, R for retransplant. And so we use P time to figure out when the actual last known status was, and then we use PX stat to figure out what that last known status was. And so we just have to clean those variables just a little bit. What we can do is first we're going to summarize P time in detail. So with the D, just taking a look at it, we see that Median follow-up time is 1,368 days post-transplant. Mean is 1,772 days post-transplant. So something to always know is that in this data, we always have to replace p time with p time equals 0.001 if p time equals 0. So this is the code that I always use. And basically what I'm doing here is we can see that in our p time data, we do have a number of values that are 0. And so what that means is these recipients theoretically died on the day of transplant. And so that's why they have essentially last known status time of 0. And remember that this is fake data, so this is not indicative of real recipient follow-up data. But essentially in our database, we have about maybe somewhere between 1% and 5% of patients who have a 0 for that P time. And what we want to do is we want to tell STATA that we do want to include these recipients in our survival time analysis, even though they died on the day of transplant. So the way it works is if their P time is 0, STATA would not include them in the at-risk population because they were technically never at risk if their P time was 0. But we want to tell STATA that they actually have some sort of P time. It's very small. It's essentially 0, but we want all those patients included in the at-risk population. And so we essentially do this in order to avoid STATA dropping these patients on survival time analysis. And so this is actually a really important point. And so the way that I manually get by it is I just give them a very, very small P time so that they are not a P time of 0, but they do have a 0.001 P time. And they're now included in the at-risk population, but on the actual curve in the survival analysis, they drop off pretty immediately. Okay. All right. So the next thing we want to do is something that I always like to do is, especially for analyses where we're doing post-transplant survival in terms of years, I like to all right, I see a question in the chat about won't that skew the results? And yes, it will, which is why we're making it really, really small. So that's why we're making it 0.001. But that is a great point because technically you are skewing the results by like a tiny bit. Theoretically, with it being so small, this shouldn't affect the analyses too much. And if you're worried about that, you can always just like make it even smaller by adding more zeros in front of the 1, basically.
Sorry, I meant you adding those patients who actually died during transplant.
Oh, got it. Yes. And so I guess that's a good point. So you're adding both patients who died on the day of transplant and patients who died, like, let's say during the transplant operation. And so that's something that you can talk with your team about and figure out if that's a population of patients that you're actually interested in. And so, for example, you do want to know, like in some instances, for example, you're looking at certain types of donor organs. And let's say you want to look at graft function from certain, marginalized or extended criteria donors, for example, and they end up dying on the table because the donor organ doesn't begin to work right away. That's an example where it's like you do want to include patients who die intraoperatively or during the operation. But that is a good point. You do want to sort of think about that and think about whether that population is of interest. But I will say there is no way of separating out those who die intraoperatively on the table versus those who like make it off the table or in the ICU and die post-transplant on that post-transplant day 1 or day 0. Okay, great question. If anyone else has any questions, feel free to use the chat. I'm just going to move ahead for now. So the next thing I like to do is I like to create a years variable. So remember this P time is in days. And so that's why the numbers are really big. But if we're interested in looking at like 5-year outcomes or something in the order on the order of years, it's easier to have a years variable. And so I essentially just create a new variable that's equal to P time. I divide it by 365.25. And then essentially that creates a new variable on the that's essentially P times, but in years. And then again, as with cleaning all data, we're gonna label it just to make it clear what this is. So follow-up time in years. Okay, perfect. And then I know we talked briefly about the pxstat variable. So just looking a little bit more at that. So pxstat. Essentially, there are four options in the UNOS database. A for alive, and alive being patient or recipient was alive at the time of last follow-up, where the time is the P time, number of days since transplant. D is for death or died. L is for lost to follow-up, and then R is for retransplant. And we can actually see that here as well. And so for the purposes of my analyses, sometimes it's just easier to have one variable for died essentially. And so I just say gen died equals 1 if pxstat equals C, run that variable, and then replace died equals 0. Essentially, we want died to equal 0 if it's not D. And so what I like to do here is I just use this command here. So instead of equal here, and remember last time we talked about the double equal sign versus a single equal sign. If you do exclamation equal sign, that's essentially saying if pxstat is anything but D. So if it's not D, then we're going to replace died with 0. Okay. And then what we can do is we can tap this variable. So we can take a look and we see that 22,240 have died, which again is exactly what we're interested in here, because that corresponds with what we're looking at. And so that is perfect. All right. And so moving on to the next portion of this. Now I'm going to move into showing you guys how I start putting together my analyses. So essentially, remember, all that we've done so far is we've just cleaned our data set, starting with baseline characteristics. And then today we moved into some outcomes as well. And now we're going to actually start putting together our results. So starting with baseline characteristics, Emily showed a paper last time of an example UNOS paper. And essentially what we want to do is pretty much most clinical outcomes papers will have a baseline characteristics table. We often call it table 1. And there's actually a very good STATA written or STATA user written code for this table 1. Essentially creating a table 1 that we can use for our paper. So table 1 MC. This is what the command is called, and it is a user written command. And so you do have to install it if this is your first time using it. And so I believe it's SSC install. Yeah, so SSC install table 1 MC if this is your first time using it. If you've used it before, you only have to install it once on your STATA and then it should work. And so I'm just going to write in the code here for what it looks like, and then I'm going to explain what everything means. So essentially, what I'm doing here is I'm writing this table 1 MC code. Here with the 3 forward slashes, you'll notice that it's green, which means it's sort of like commented out, like it's not actually part of the code. And what this essentially tells STATA is that it's telling STATA that I'm artificially inserting a line break here, but to not actually consider it a line break. So theoretically, this code here with the 3 slashes is exactly the same as if I didn't have 3 slashes. But for the purposes of this, I like to include these 3 slashes just because visually it's easier to see what's going on. And so that's how I typically make all of my table 1s, is I will insert 3 slashes here. I will put one variable here, and then insert another 3 slashes, put my next variable here. So recipient race, for example, and then insert another 3 slashes and essentially end the table 1. So end the code with an end parentheses. And so this is all technically one line. I'm just telling STATA that I'm artificially putting it in multiple lines. And when we run it, we want to highlight everything at once to run it. And so going through a little bit more. So table 1 MC, that's the actual name of the command that we're doing. Here, vars is essentially we're telling it what variables that we're interested in So vars open bracket or open parentheses, We're going to go to the next line, and we're essentially saying we want age as the first row in our table here. And then cont s. So this is essentially where I'm telling Stata what kind of variable this is. So cont socio nt essentially means for continuous, and then s, I like to think of it as s for skewed. And so this is essentially running your descriptive statistics, or in the case of this, we're just summarizing data here. So since it's skewed, we're going to report it in medians, which is what this code is going to do. If this was a normally distributed variable, we do cont n for normally distributed, and it would instead report the median. But since I know that in this variable, or in this data set, age is skewed, I'm going to do cont s. Here with the percentage sign 4.0f, essentially I'm telling Stata how many decimal points to include. And so really the number that I'm interested in is the one number after the decimal point. Here I'm telling it to include zero digits after decimal point, just because for age, we're just interested in whole numbers here. So we don't care if it's 60.1 versus 60.4. We're just going to write 60 for that. And then the same thing for the next variable. So here, recipient race, this is the new variable I created from our last session, and that is a categorical variable. So I just write cat here. And then last time we also cleaned recipient male. So we can go ahead and include that here as well. So recipient male, and this is a binary variable. So this is a 1, 0. And so here are the three most common variable types. We have continuous, skewed variables, binary variables, and then categorical. And then we can go ahead and run this. So perfect. And then one call here, I'm just telling it to put it all the variable names into one column so that it's easier to read, basically. But what we see is we can see a good summary of our data. So of 38,000 patients or recipients in our database, median age here was 62 years, and it's reporting the IQR, so the 25th and 75th percentile, so 51 to 72 years. For recipient male, 58.4% were male in this data set. Recipient race, this was the breakdown for race. And so this is actually just a really easy way to kind of put together your baseline characteristics. If you're just trying to describe your, for example, your patient population that's included in the study, this is how you would do it. And then typically you're going to have two comparison groups in your study. So you're going to have comparison group A versus comparison group B. And for your baseline characteristics, you really want to compare those groups. And so the way you can do that is with very similar code. But before vars, you're going to add by. So let's say for the purposes of this analysis, what we're interested in comparing is female and male recipients. So we can add by recipient male, and then space vars, and then everything else is exactly the same. And so we can run this. And essentially what we're going to do is we're going to see everything as a comparison by recipient male. So the left column here is recipient male equals 0 or female, and then the right column is recipient male equals 1 or male. We can see that the recipient male variable is distributed exactly as we want it to be. So 0% for female and 100% for male. And then age, we can see that male recipients in this data set were older, so a median age of 64 years versus 60 years. That was significant with a p-value 0.001 or less than 0.001. And we can see that recipient race is not different between male and female recipients. So this is how you can very easily make your table one. So essentially you'd put all of your variables of interest here in your code, and then you can pretty easily it'll essentially just run all your descriptive statistics as you normally would, but it saves you time from having to run each one individually and then copy and paste each one individually. And then the other cool thing about this is you can actually save the data. So if you change your code, you just add the word saving to it, and then you can actually say, like, give it a name, table one, XLXSX, which means save it as an Excel sheet format, and then you rerun it. Essentially, what you're doing is, does that already exist? Okay, so we can say, we'll tell it to. Okay, perfect. So essentially what we're saying is to rerun it and then save the output. So essentially save this data as a table one. And so what you can do is you can go to your STATA directory. So whatever folder you use to put all of your output in when you change your directory, you go here, you see that there's a new data set called table 1, click on it, and essentially it brings you to an Excel sheet, hopefully. And then on the Excel sheet, then you can essentially just copy and paste it into a Word document. So perfect. Okay. So it's going to have me log in, so I'm just going to leave it for now. But what you can see is essentially it's in a very easy to deal with format where you just copy and paste it into a Word document, and then you can go ahead and use that in your results section. And so table 1 MC, a great way to do baseline characteristics that saves you a lot of time. And essentially it does all your typical descriptive statistics. There's a description of this code online, and so you can go ahead and take a look at that. Yes, great question. What is the research question for this example? So there's, I guess, no research question. I guess we can say for this example, we're comparing like male versus female recipients and outcomes, basically. So comparing outcomes for male versus female. I believe these were lung transplant recipients in this example. And so what we're doing is we want to essentially look at baseline characteristics. We don't actually care about recipient male here. All we really care about is looking at sort of baseline characteristics and saying, okay, in our cohort where we're comparing male versus female, males are older on average, or median age is older, and then, have that play into sort of further analyses, multivariable analyses. Okay, so let's move on to regressions. So regressions, essentially, we can go through some of the basic ones. So we'll go through, for example, logistic regression. We'll go through linear regression. We'll go through Cox regression. And you'll remember from your basic stats classes that logistic regression, you're essentially looking at the effect of independent variables on categorical dependent variables, so categorical outcomes. For your linear regression, you're looking at the effects of independent variables on continuous outcomes, so continuous dependent variables. And then Cox regression, this is your survival analysis. And so starting with logistic regression, remember we're looking at categorical outcomes here. If we look at the outcomes that we cleaned, we see that intubated at 72 hours is a categorical outcome. So it's binary, which is also categorical. And so for intubated 72 hours, that's what we're going to use. We're going to use logistic regression. And the code for logistic regression is simply log it, and then we put our outcome of interest here. So remember, categorical binary outcome, and then our variable that we're interested in. So for example, in this analysis where we're comparing outcomes of male versus female, we can say recipient male is what we're interested in. And this here is a univariate analysis where we're just looking at the effects of recipient sex on intubation at 72 hours post-transplant. And what we can see, one other thing is for logistic regression, we typically want odds ratios. And so if you add comma OR to the end of it, then it'll give you your output in odds ratios. So you'll see recipient male odds ratio of 0.74, 95% confidence interval of 0.70 to 0.79, or 0.79, with a p-value of less than 0.001. And so essentially what this is telling you is that in our data, being a male recipient is associated with a lower odds of being intubated at 72 hours post-transplant. And so that's an interesting finding. It's a significant finding, but we do want to also account for potential confounders. And so this is when multivariable analyses come into play. And so how you would do a multivariable analysis, it's very similar to the univariate. Essentially, log it 72 log it int 72 for the outcome. Put your variables of interest here. So recipient male is what we're interested in. but we do want to control for other variables. So we can control for age, we can control for race as well. Now, race is a categorical outcome, and so the way we do that in STATA is we need to add an I dot in order to tell STATA that it's a categorical variable, actually. And so when we run this, where we include the I dot for recipient race, what it does is it takes one category, typically the first category, as your reference category, and then it compares all of the other categories to that reference category. And so for race, what you can see is that it took white race as the reference category, and then now it's comparing all the other categories to white race. And you can see that it gives you an odds ratio for each one, along with a 95% confidence interval and a p-value as well. And remember, if it crosses 1, then it's not significant. And then we again can look at, so recipient male, that was what we're interested in, our main variable, or our main exposure of interest essentially. And we can see that even after adjusting for age and recipient race, it's still significant with an odds ratio of 0.77 and a p-value of less than 0.001. But here's essentially where you would go ahead and add in all the variables that you're interested in adjusting for. And typically you either decide that with your team ahead of time as to what variables you would want to control for, or you can decide it with some statistical methods like doing other univariate analyses and stuff like that. But essentially that's how you would do your multivariable logistic regression. And then moving on to linear regressions. So remember, this is for continuous outcomes. So in our example, what we're going to do for this one, how we're going to show this is with length of stay. So looking at essentially effect or association between recipient sex, so male versus female, on postoperative length of stay, post-transplant length of stay. And to run a linear regression, the code is just regress. And then again, we put our outcome of interest, or continuous outcome length of stay, and then our exposure of interest recipient. And so this is what we get. We see that that there's a coefficient of negative 1.36, and this also is significant. Similarly, if we wanted to control for other variables in a multivariable linear regression, we would just add on the other variables afterwards. So same exact thing, and then this is your adjusted coefficient here that you're interested in. So very similar between linear and logistic regression. The last one I'm going to show you is Cox regression. And so this is your survival time analysis. So this is slightly more complicated because we need to essentially put your data set in survival time, formatted for survival time analyses. And so the way you do that is you use a command called stset. And I recommend that everybody, when using this, just go ahead and read the help manual for what this actually is and really try to understand what's happening here. But just to show you as an example, what you do is you write stset, and then you put in your post-transplant, your follow-up time essentially. So remember, we cleaned p time years, say essentially follow-up time in years. You set in origin time, so time 0, I'm just going to say, and then in enter time. So again, time 0. So just telling STATA that we're interested in entering at time 0 or time of transplant for each recipient in our data set. We're going to set an exit time. So for example, if we're looking at 1-year survival, we can say that we're going to have everybody exit at 1 year, just to look at 1-year survival. And then you have to tell STATA what the failure is. So in this case, since we're interested in survival, we're telling STATA that the failure is death, or our variable died. And then so you just run this to essentially ST set your data, or put your data in the right format for survival time analyses. What you see is that when you run this, you have a few new variables here that didn't exist before. So underscore ST, underscore D, underscore T, underscore T0. These are all variables that STATA created when you ran this command, essentially in order to put your data in the right format for survival time analyses. And then from here, you can do a number of things. So for example, if you want to perform a log rank test. So we're comparing effect of recipient sex on 1 year post-transplant 1-year survival. And so we can run this command. So STS test, recipient male, and then log rank. So this is essentially to perform a log rank test. We see that the p-value is 0.05, so right on the cusp there, not technically significant. And then in order to run a Cox regression, so how we would do that is we would say ST Cox recipient male. So very similar to the prior regressions, you want to run, so the actual command is ST Cox. And then because the outcome is survival itself, you don't have to put an outcome variable in there. You just put in your exposure of interest, which for us is rec male. We can run that and we can get a hazards ratio here, 1.05. Again, right on the cusp of significant but not significant. And then the 95% confidence interval. It does cross 1, so it's not significant. And so what this output is telling us is that recipient male is not significantly associated with 1-year survival in this analysis. And then if you want to do a multivariable Cox regression, very similar. So you just run the same command, but you add on all the variables that you want to adjust for. So let's say age and recipient race. And then you run that, and what you can see here is that after adjusting for age and recipient race, and again with recipient race, you want to add the I dot here in order to tell STATA that it's a categorical variable. Essentially what we see is that that recipient male is, it's even less significant now. So it's a p-value 0.13. And so this is your adjusted hazards ratio after adjusting for age and recipient race. And so that would be your multivariable Cox regression. This here is your univariate Cox regression. In order to take a look at actual Kaplan-Meier survival, essentially, what you're going to do is SCS list, and then we can say by recipient male here in order to tell STATA to group it by male versus female, and then risk table 0 and 1. So this is essentially asking STATA to tell you what the estimated survival is at time 0, so at time of transplant, and then at time 1, or 1 year post-transplant. And so what you can see is at time 0, so for recipient male equals 0, so this is for females, your survivor function is 1. So essentially you have 100% survival at time of transplant, which makes sense because that's the time you're starting to track them. And then at 1 year, you have 86.3% survival. And this is for females. And then for males, where recipient male equals 1, you have 100% survival at time 0. And then you have 85.6% survival at 1 year post-transplant. And then if you wanted to actually take a look at the Kaplan-Meier curve, so you want to visualize your outcome. Essentially, you can use STS graph. You can tell it to graph it by recipient male. And so if you run that, essentially, it takes a little bit to load, like a second or two to load. And then once it loads, essentially what you see here is you see one line for recipient male equals 0, so female in blue, and then male here in red. And essentially this is your Kaplan-Meier curve. The curve looks a little odd because essentially when I created this fake data, the way I manipulated it, a lot of our recipients had a p time of 0 essentially, so they died basically on the day of transplant. But in reality, when you do this on real UNOS data, you'll see a much more rounded curve here, and it makes a little more sense. But essentially, we're looking at here on the x-axis time, so from 0 to 1 year, and then on the y-axis our survivor function, so 0% survival, and then 1 year 100% survival, and then we see that it goes down to about 86% here. And so what you can do is you can actually look. You can use the command window. You can say help STS graph. It pops up the STATA help command, or the manual essentially for your graph for the survivor or related function. And then essentially this is where it tells you how to essentially change things on your graph. So there are a number of things we can do. For example, if we wanted to add confidence intervals, we could add the command CI. It would add confidence intervals here, essentially showing 95% confidence intervals, stuff like that. You can change your graph in other ways to make this look pretty. So for example, you could change the way your axes look. You can change the range of the axes. So instead of 0 to 1, you can, for example, just do 0.75 to 1, and that way you can see the lines better, stuff like that. So you can play around with your actual code, but this is the baseline code for visualizing your survivor functions, essentially your Kaplan-Meier curves. And then the cool thing about this, so let's say that this is the graph that we want for our paper, or actually, let's actually just get rid of the confidence intervals. And let's say that this is the graph that we want for a paper. For your own analyses, I'd suggest, making the graph yours, changing it so it looks nicer as opposed to this sort of base graph here. But what you can then do is you can then export it. So you can export it with this command. So graph export, and let's call it example Kaplan-Meier. And you can export it as a PNG. So as PNG, this is essentially telling your code what to name the file. You want it as PNG. You give it a width in pixels, and then you can say replace if it already exists, or you can just run it without replace if it doesn't exist yet. You run that code. Essentially, you need your graph window actually still open in order for this code to work, because it essentially exports whatever graph window is open. And you can see here that the file has been saved in PNG format. If you go back to your folder here with all your outputs, essentially what you do is if you open that PNG file, something is wrong with it. It's not opening. I'm pretty sure it's right though. We should be able to open it, but for whatever reason, it's just not opening right now. But essentially you can use this file for your manuscript. That should work. And then essentially that is kind of your basics in terms of coding. So essentially, in summary, what we did was we imported our data set, we applied inclusion exclusion criteria, we cleaned our data set, we did baseline characteristics, so cleaned our baseline characteristics, cleaned our outcomes, we ran a baseline characteristics table using table 1 MC, a great user written command for STATA. And then we did some regressions as well. So logistic regression for our categorical outcomes, linear regression for continuous outcomes, Cox regression for our survival analyses. We even made a quick Kaplan-Meier curve here, and we learned how to export the data and export the file. Any questions?
I have one quick question. You did it so fast that I didn't notice. In order to run the file, you highlight it and do you push enter?
Yeah, so you highlight it and then you push Command D if you're on a Mac, or Control.
Gotcha. Or control D if your words. Okay.
Exactly. And then you can also hit this button up here,
Gotcha. Thank you.
and then it'll run whatever code is highlighted. Yeah.
And then how did you learn about this? Like, because the way it just flows so easily. Like, did you take a course?
So honestly, a lot of it was just figuring it out sort of on my own, and working with some like great mentors who really helped me. A lot of it, which I can actually stop my screen share and then share some slides now as well. So let me share some slides. So kind of just picking up where we left off last time. Just some tips, but to answer your question, yes, I didn't take a course, no, so I didn't learn formally, but it was kind of just a lot of learning from residents as I went, learning from other medical students, Googling a lot, kind of figuring it out through trial and error, and then also just practice with projects. And the first project you're going to do is it's going to take a lot of time because you're going to have to go through and clean all your data. But let's say you do one project from start to finish, the second time you do it from start to finish, especially if you're using the same data set, you can reuse a lot of your code. And so it goes by so much quicker the second time around. And then each time you do it, it gets easier and easier.
Thank you.
Yeah, absolutely. So just going over some quick tips in the last few minutes that we have. So some tips that I sort of came up with and that I've learned from trial and error and lots of failure along the way over these last 5 years or so. So I started STATA around 2020, so it's been about 5 years now. So always save your do files as you go. So no need to save your data set. So if you notice, I made a lot of changes to my data set, but I never actually saved the data set itself. And the reason I don't do that is because I don't want to overwrite the data that I have with the changes that I made, just in case the changes, just in case I want the original data. So for example, if I exclude a bunch of patients, I drop them from the data set, but for another project, I actually do want those patients. I don't want to actually permanently change the data. So what I do is I always save my do file as I go, and then I always keep the same original data set. So that way it's always reproducible. So every time I open a project, I essentially open the same original data set. I manipulate it the same way every time using my save do file commands. And then I save the do file, but I never actually save the data set. And this way you also don't have to make, multiple copies of your data set over and over again for each project. It saves space on your hard drive or whatever drive you're saving your data on. But again, the key is to always save your code so that your data set and your analyses are reproducible every time. Next tip, so utilize the help command. So I showed you this a little bit at the end with the STS graph example, but essentially if you go to Stata and you write help and then type in the command that you want help with, it will display essentially a manual for how to use that command. It'll show you essentially data, or it'll show you information on how to actually write it, so the syntax, but it'll also show you examples sometimes for how to use it in Stata. And so whenever I have a question with a command, that's usually the first thing I'll do is I'll pull up the help command. I'll take a look at what the manual actually says for that command, and then I'll try to figure it out. And if I can't figure it out from there, then I go to Google and other resources. So my third tip is to think about the end product. So before you start your analysis, think about what you're hoping to analyze. Think about what your exposure of interest is, what your outcomes of interest is. And oftentimes it's actually really helpful to have essentially shell tables and figures before you start your analysis. And so, for example, you can create a table 1 and say, column 1 is group A, column 2 is group B, column 3 is your p-value, comparing them. And then write out every variable that you want in your baseline characteristic table. And that way, when you type it up with your table 1 MC code, you can just go down the list, have your shell table on one side of your screen, your Stata on the other, and just go through and type it in exactly how you want it to be. And so that's really helpful. And same thing with, logistic regression, linear regression, Cox regression, all of that. If you make your tables ahead of time, figure out which odds ratios and hazards ratios you're interested in, and then, have them out in your table. And then all you do is you run the command in Stata, you look at it, and then you just type in the results in your Word document. Next tip, code in sections. So if you notice today, essentially when I was demonstrating cleaning the outcomes variables and running the regressions, I would code one line at a time and then run that one line at a time instead of coding, an entire do file and then running it all at once. And that's just, it's an easier way of doing things. So you can write a bit of code, you can test it. If there's an error, you can debug it, you can figure out what's going on, and then you write a little more, you test it, debug it, and so forth. And that kind of goes into the next tip as well, which is to always check your work. And so you'll notice that every time I cleaned a variable by essentially creating a new variable, I always checked it afterwards to make sure that the new variable was what I expected. So if I wanted, if I was trying to make a new variable for recipient sex and make it rec male, for example, always checking to make sure that the old variable and the new variable correspond with each other. And so that way you're not, artificially introducing sort of new or made up data by making mistakes in your code, basically. And so always check your work. You can do it like I did it, which was to always tab your new values, take a look at it, make sure it aligns well. You can also, compare new variables, if it's not something where it's a direct comparison of old versus new variables that you're making, you can compare what you find to prior studies with known literature. For example, if you're expecting a certain diagnosis to be in, for example, 60% of your population, but you're seeing that it's in 2% of your population, then you might think a little bit about how you're coding and whether or not your code is correct. And then the other thing is you can look at individual cases to see what actually happened. So you can browse, you can open up your actual data by looking at the browse window. And then as you're running the code, see what happens to individual data or to individual cases. So if you're trying to drop, for example, if you're trying to only look at lung transplants and you're trying to drop all heart transplants, you can actually open up your browse window and then run the command and see all the heart transplants in your data essentially disappear. And so that's a good way of also just making sure that what you're doing is right and checking your work. Just a few more tips. Tip number 6, regularly check for missing data. So this can really affect your analysis. And oftentimes when you code and you just look at things, you don't actually see the missingness. All you see is the data that's there. And so you always do want to be checking for missingness in your data, understanding, what data is missing, how it's missing, and how that affects your analyses. So for example, for intubated at 72 hours outcome, remember that I said that this variable only became very available in 2015. And so essentially when we're running that logistic regression, it's dropping anybody with missing data for that variable. And so essentially for that actual example outcome analysis we looked at, it's that part of the analysis only included recipients from 2015 onwards. And so that's just something to keep in mind is that missing data can really affect your results. Tip number 7, stay organized and reproducible. That's kind of key to all of this, is to just, every time you update your analysis, just make sure you know what you're doing, make sure it's reproducible. That'll save you a lot of time in the future, especially if you're sharing your analysis with other team members or you're going back months later for a revision. And you can use commenting generously as well. And so that's just, notes to yourself about how you're coding the data and what you're doing and why you're doing it. And those were all my tips. And then some resources. So this is going back to the earlier question for how I learned. So one of the resources that I love is Data Wrangling in STATA. And this was essentially what I used to learn my basics data. And so it's this website here. Essentially, they have a bunch of modules here. So you start with an introduction and review, reading your data, first steps with your data, all of this. And what you'll see is a lot of it is similar to what we covered. So how to gen new variables, how to replace variables. And essentially, this is how I learned how to code and how to use data. Yes. So I would recommend, what I did was I just spent, a few nights going through each of these modules, and they have actual example files that you can download. You can follow along and then see if your code matches theirs. And they go through very good basics. They also go through a little bit more complicated stuff like restructuring data sets, combining data sets. So we didn't really cover any of that today, but this was super helpful. And then other resources, the help command in Stata. Stata list is a Stata forum. So it's kind of where people go and ask questions. They have really strict community rules. So I would just keep that in mind in terms of, when you're asking questions, always use your full first and last name, stuff like that. But sometimes I'll just Google questions and Stata list will pop up, and it's helpful to see what questions other people had and how people fixed it. And then also Google and ChatGPT, especially the newest version of ChatGPT, is very good in terms of helping you with code. So would definitely recommend. And yes, here is the link to the Data Wrangling in Stata resource. Okay, so I know we're pretty much right at the end of our time. Does anybody have any questions? Where can we access this recording? Isaac or Carter or Emily, do one of you know where the recording's going to go?
Yeah, this recording will be with the two that preceded it on the TSMA website. It will also be on YouTube. Thank you. But it should be accessible at least to the YouTube links via TSMA website. There's all kinds of other stuff on there too that all of the different committees has done. Just a little plug for TSMA there. But yeah, these should be accessible very soon after we wrap up here.
Yep. And you'll find the prior recordings as well. And so you can also, if you didn't go to the last session, for example, you can take a look at that one as well. Okay, perfect. Any other questions? All right. And feel free to reach out. I'm going to paste my email in the chat. Feel free to reach out if you have any STATA questions. Always happy to help. And thank you all so much for attending. All right. Have a good night, everyone.